My recording seems to have gotten a little bit cut off, so let me actually redo all of this again. So we have that for us to find the position of s of t at 1 for 1 second and 3 seconds, then all we have to do is substitute into our formula from above. So that's negative 16t squared plus 96t. And I'm going to first look for s of 1, and then I'm going to look for s of 3. I'll do it this way. So I'm going to be plugging in 1 at first. So I have negative 16 times 1 squared plus 96t. So that means that s of 1 equals negative 16, because 1 times 1 is 1, and negative 16 times 1 is just negative 16. And 96 times 1 is just 96. So we have negative 16 plus 96. That means we have 96 minus 16, and that should be 80. And remember, this is in feet. So we have 80 feet. And then for S3, when we plug in 3 into our function, we have negative 16 times 3 squared plus 96 times 3. So that means we have the following. We have negative 16 times 9 plus, let's say this is 3 times 6 is 18. 3 times 9 is 27, so that's 28. And S3 equals this 56. Oh. So this equals negative 144 plus 288. And this is equal to negative 144 plus 288. That should be positive 144. So now we have the position of both the rock after 1 second and the rock after 3 seconds. Now to compare to find the average velocity over this time interval, all we have to do is figure out what the change in the position is divided by the elapsed time. So we have to basically, if you remember the slope formula we covered last week, the slope formula was the change in y divided by the change in x. In this case, for this particular problem, what we're going to do is for velocity, we're going to take the change in the first value that we had. Let's call that, t1 minus the change in, or the position of t2 divided by t1 minus t2. And just to make our computations nicer, I'm going to say that t1 and the t1 is just 3. So s of t1 is just going to be 144. That way we don't have to deal with negative numbers. We're going to have 144 minus 80 divided by 3 minus 1. Now 144 minus 80, that is 64 feet. Remember, this is all in feet and seconds. 3 minus 2 is 2 seconds. So we have 64 divided by 2, that's going to be equal to 32 feet per second. So we have found that the average velocity for this pair was 32 feet per second for the rock between 1 second and 3 seconds. Now we could do the same thing between the interval 1 and 2. So we already found what t of 1 is, or what actually s of 1 is, so we don't have to do that again. But we do need to check for what s of 2 is. So let's do that right now. So for 2, we know that t of 1, when t is 1, we get 80. So I'll just write this down for reference. We have 1 and 80. Remember, this is t and this is s for this problem. So what we're doing now is going to look for s of 2. And again, the formula is negative 16t squared plus 96 times t. So we're going to have negative 16 times 2 squared plus 96 times 2. Well, this is going to be negative 16 times 4 plus 2 times 96. I believe that's 192. S of 2. And then 16 times 4, that should be negative 64. So we have negative 64 plus 192. So now all we have to do is subtract. So we have S of 2 is 192 minus 64. So that should be 128. I believe that's 128. So now, what we can do is the following. We could do the same situation. We're going to find the slope, or the rate of change. And again, that is the change y with change in x. So it's going to be 128. Well, let me actually write it the other way so you can see it better. Again, that is, the position, as t of 1, minus the position of the second time, divided by the difference in time. So this is going to be 128 minus, and we said that this was 80 before, divided by 2 minus 1. So it's going to be equal to 128 minus 80 divided by 2 minus 1. So we're going to get 2 in the denominator, and in the numerator we're going to get 48. Yeah, 48. So it's going to be equal to 48 feet per second. So now we have actually found what the average velocity is between this time interval 1 and 3 and the time interval 1 and 2. Now, let me just show you really quickly on GeoGebra how this actually is shaping out. So this is not the graph of the rock. This is a graph of the change in velocity for the rock. Because remember, the rock is being thrown up, and gravity is going to bring it back down. So it's going on basically a vertical line. So we have, and I'm going to use x's here because I don't feel like changing my axis. So negative 16, and instead of t, I'm going to use x. So negative 16 x squared plus 96 times x. So we get this neat picture here. As you can see, it's going to be a parabola, and it's going to be frowning because we have a negative leading coefficient. And look how high this goes. It goes up very quickly and then down very quickly. And we actually found out what the values were for between 1 and 3. So we know that at 3 we had 144 feet. So at 3 we get our highest value. So that should be probably the vertex for this. We could actually check that. And then for 1, we had, what do you have for 1? 80? Yeah, for 1 we had 80, and for 2 we have 48. Well, what am I doing? I'm not zooming in. Let's zoom in. Maybe I should just put the points. So yeah, let me put the points, so that will make it look better. So we have 3 and 144. And then our next point was 128, not 80, 128. And then the third point we had was 1 and 80. So we had 1 and 80. So here we could see the points that we plotted. So after 1 second, you're moving at 80 feet per second. After 80 feet per second. After 1 second as a lap, you are up 80 feet in the air. After 2 seconds as a lap, you are up to 128 feet. And then you reach your climax at 144 feet, and then you come back down. And this all happens in the span of, I believe that looks like 7 seconds. I keep zooming in this way. I need to change my settings so I can zoom in better. Oh, that's 6 seconds actually. So yeah, this also happens in the span of 6 seconds. So if somebody asks you how long does it take for the rock to reach the ground, you could tell them that it takes about 6 seconds, because at 6 seconds you're back at 0. So that actually shows what the average velocity is of the slope between all of those points. Now, what happens when we have something like this? If you notice the difference between the 2 points, if we were to plot a line between them, let's say between point A and C, this is when we did t equals 1 and t equals 3. If you notice that line, this particular line goes on the inside. Let me actually change the color so it looks better. Okay, red. So if you notice, this red line goes through this point and then goes inside of the function, and then goes through, and then goes through the point A on top. We call this a secant line. A secant line goes between 2 points in a function. That's like a very, very loose way of defining it. We will see examples of secant lines throughout the course, but we will also see and spend more time talking about the so-called tangent line. So as we move forward, we'll begin to be able to actually plot this graphs all semester long very nicely. So let me define what a secant line is right here in the notes, very loosely. So a line passing through 2 points on a curve is called a secant line. So whenever you have a line that passes through 2 points on a curve, you have a secant line. Let me give you an example, like a more local example. Let's say you have this function, something that looks like this. Let's call that f. Let's say you have point A here and point B here. Then a secant line will be a line that goes through those 2 points, kind of like this. That will be a secant line. And I'm going to define it now, but we'll see it later on in the semester, like in a month from now. A tangent line is a line passing through just 1 point. So let's say if we had this green point here, then a tangent line will be the line, and please don't close on me. Hold on. Oh boy. Let's reopen this. As I mentioned in the first video, this will happen often. It's a Microsoft whiteboard just continues to crash on me. Luckily, it saves all the work. So yeah, so any line passing through 1 point on a curve, and I did not want to use this color. This is called a tangent line. So this one, it's called a tangent line. This one is a secant line. So these are two very, very important concepts to know. So let's really quickly talk about the instantaneous rate of change, or instantaneous velocity. So what we're going to do now, we will estimate the instantaneous velocity of the rock at the point t equals 1. See, when you compute the average velocity, we use 2 points. When we compute the instantaneous rate of change, or the instantaneous velocity, we only use 1 point. So this is important to know. When we find the average velocity, like we did in the first example, we use 2 points, or 2 ordered pairs. And when we find the instantaneous velocity, we use a single point in time. So instead of using 2 points, now we're going to use 1 point. And we're going to do this at the point t equals 1. Now we know what s of 1 is. We calculated s of, that was the first thing that we calculated. S of 1 was just 80. So let's talk a little bit about this. So remember that when we compute the average velocity over an interval, so if we compute the average velocity over the interval 1 and t, then we have to use the following formula. And I'm going to keep using m for slope, because essentially what we're doing is finding a slope. Now we're going to take, again, the biggest value, in this case is t. We're going to find its position. We're going to subtract 1, smaller value, and then we're going to do t minus 1. Again, this is what we've been doing so far, changing y over changing x. The change in position divided by the change in time. So here we notice that we don't have a value for t. We have a value for 1, we have s of 1, but on the upper limit, or the upper bound, whatever those words mean, we don't have an actual value. So what we're going to do is we're going to make estimations, because we want to find out what happens at 1. So we have to get closer to 1. We have to find values that make us very close to 1. And for this, I'm actually going to make a table. So we're going to call this, let's say, time interval. And I'm going to call this the average velocity. So we want to go to 1 and t. We want to find out what the average velocity is, or the instantaneous rate of change is at 1. So when you are just at that one single point, we want to find out what that velocity is. We already found out from the previous example what the velocity is for the interval 1, 2. If we go back up here, we also find it for 1, 3, but I don't want to go up that high. For 1, 2, we had that it was 48 feet per second. So we found out that this was 48 feet a second. Well, what can we do now? We could keep making the time interval smaller. So instead of going to 2 seconds, we're going to go to 1.5 seconds. And then, 1.1 seconds, 1.001 seconds, and so on. So we'll continue this until we get very, very close to 1. And you'll see what I mean by getting very, very close to 1. So I'm going to calculate this for you. Okay, so let's calculate first 1.1 to 1.5. So we had s of 1.5 minus, again, s of 1 divided by 1.5 minus 1. So all we need to really worry about here is what s of 1.5 is. To find what s of 1.5 is, we have to use the formula given above, which is, negative 16 t squared plus 96t. Now, I'm not going to bore you through this because we already, this is from pre-calc. I mean, plugging into these functions, it's a pre-calculus concept. So I'm not going to spend too much time actually plugging in when I don't have to. I'm just going to use GeoGebra. So we have negative 16, 1.5 squared plus 96 times 1.5. So that's 108. So we have 108 minus 80. So it's going to be equal to 108. So we have 108 minus 80 divided by, well, 1.5 minus 1 is just 0.5. 108 minus 80, I believe that's 28 over 0.5. So that should be what? 28 times 2, that's 56. Yeah, so that should be equal to 56 feet a second. So now we see that the average velocity has increased as we move closer to 1 second. So what we're really trying to find out is how quickly is the rock moving at 1 second. So we'll continue to do this. So let's do it for 1.1. So first, let me real quick find what s of 1.1 is. Again, we're using the same formula. So s of 1.1 will simply be 86.24. So we have 86.24. And now the slope for this one is going to be s of 1.1 minus f of 1 divided by 1.1 minus 1. So now this one is going to be equal to 86.24 minus 80 divided by 0.1. So this is the same thing as 6.24 divided by 0.1, and that should be equal to 62.4 feet a second. You could verify that on a calculator if you don't believe me. Simply divide 6.24 by 0.1 and you should get the result. Or again, change this into a fraction and you'll again get the result. There'll be 1 over 10, then keep change flip and you'll get 62.4. Please don't close on me. And it closed on me again. I'm definitely going to need to get a new whiteboard because I don't want to keep you guys saying this crash all the time. And I'm not going to edit this out. Believe it or not, last semester I used to edit that out and people actually complained because I edited it out. So yeah, can't please everybody. So 62.4 feet a second. And we could continue this in the same process. I'm actually not going to continue the same process. I don't want to make this too long. But for the next one, the result should be 63.84 feet a second. And then, let me just rewrite this, 1.001. That's going to be 63.984 feet a second. And if I were to go one more decimal expansion closer to 1, if I make this number smaller, then I will get 63.9984 feet a second. So as we could see, the closer we're getting to 1 second, the closer we're getting to 64. Notice we began with 48, then 56, 62, 63, 63, 63. And now it's, getting very, very close to 64. So, as we can see, the closer our interval, our time interval, gets to 1 second, the closer the average speed, or not speed, it's velocity, average velocity gets to 64 feet a second. Later in the semester, meaning the next video, we will say that the limit of the velocity as t approaches 1 is equal to the instantaneous velocity which is 64 feet a second. So this is something that we're going to see in the next video. We'll get used to using this language when we are describing limits. Again, the idea here is that we're getting very, very close to a number. If I had continued on, if we picked a number even closer, then you will see that this is going to be 63.99, maybe another 9 here, feet per second. So you could continue this process, and you will see that the closer you get, the smaller you make this interval, the closer you get to 64. Okay? Now, I just want to mention, I know I already mentioned it, but this 64 feet a second we'll see eventually as the slope of the tangent line. So I'm going to explore that right now. At t equals 1. So eventually we will see what tangent lines means. We will need the derivative for most of the computations with tangent lines to make our lives easier. I mean, you could always estimate it, but the functions that we'll be dealing with in this class are going to be very messy as we move along, so you definitely don't want to do this by hand. Thanks for your attention.